Real-world economic relationships are constantly shifting. Markets move, production scales alter, and supply chains fluctuate. These variables rarely follow simple, straight lines. In basic algebra, we model relationships using the standard linear equation, y equals a plus bx. The defining characteristic of a linear model, like the blue line shown here for y equals 2x plus 2, is its constant slope. You calculate this by picking any two coordinates and finding the change in y divided by the change in x. But when economic data creates a curve instead of a straight line, the rate of change is no longer constant. The moment the line bends, the two-point slope triangle fails. This presents a mathematical problem. How do you calculate the slope of a constantly curving equation? The solution requires a shift in perspective. We stop looking at the distance between 2 points, freeze time, and examine one single, specific coordinate on the curve. At this exact coordinate, we find the tangency point. We draw a straight line that perfectly touches the graph without crossing it. The slope of this specific tangent line gives us the instantaneous rate of change for that exact moment. Notice how the angle of the tangent changes drastically depending on its position along the curve. Differentiation provides the mathematical engine to locate this moving tangent line, extending our algebraic tools into calculus. To calculate this tangent line, we use Leibniz notation. We replace the discrete delta with the continuous d. We read this dy over dx, the derivative of y with respect to x. It denotes the exact rate y changes in response to x. The core algorithm is the power rule. Start with y equals x to the power of n. First, bring the exponent n down to multiply in front. Then subtract 1 from the exponent. The result, n times x to the power of n minus 1. Here is the rule in action. Y equals x to the 7th reduces to 7x to the 6th. The rule also governs negative exponents. Y equals x to the negative 4 resolves to negative 4x to the negative 5. This rule transforms a power function into a formula capable of calculating exact slopes at any coordinate. This leaves an obvious gap. What happens when the equation lacks a variable entirely and is just a plain constant number, like y equals 10? Geometrically, a constant number represents a flat horizontal line on a graph. A horizontal line has zero gradient, it never changes. Therefore, the derivative of any constant number is always 0. Look at the derivation shown here under the constant rule. Mathematically, y equals 10 is identical to 10x to the power of 0, which proves algebraically why the slope zeroes out. What if a constant is attached directly to a variable, like y equals 3x to the 5th? The notes break this down. Leave the constant, the 3, completely alone and apply the power rule only to the variable, x to the 5th. Finally, multiply the resulting derivative by the original constant, giving you a final calculation of 15x to the 4th. Standalone constants differentiate to 0 and vanish, while constants attached to variables act as multipliers that carry through the equation. We can now address the final mechanical hurdle, differentiating a long equation where multiple functions are added or subtracted together. The sum and difference rules dictate a straightforward approach: differentiate each function separately and then recombine them. This example from the lecture text illustrates the sum rule. Y equals x to the 6th plus x to the 7th plus x to the 8th. To solve this, you break the equation apart into isolated blocks. Apply the power rule to the first term, dropping the 6 down to get 6x to the 5th. Simultaneously, apply the power rule to the remaining individual terms. Finally, recombine the newly differentiated terms using the exact arithmetic signs from the original equation. Because the derivative operator is linear, even complex polynomials can be dismantled into simple, isolated calculations. Look at practice question 4. It combines these rules into a single problem featuring constants, negative exponents, sums, and differences. We execute a rapid derivation sprint on the first half of the equation using the constant multiplier rule. 2x to the 4th becomes 8x cubed, and negative 2x squared becomes negative 4x. Continuing the sprint, positive 3x to the negative 3 becomes negative 9x to the negative 4. Finally, the double negative on the last term results to a positive 16x to the negative 5. The final fully differentiated slope equation is now complete. We began this process needing two distinct points just to find the slope of a rigid line. We now possess an algorithmic machine that generates a master equation for the exact slope of bending curves. Mastering these polynomial rules allows us to pinpoint instantaneous rates of change, providing the mathematical framework necessary for advanced economic modeling.